let's think about category theory again. So last time what have we done? So we talked about what a category is, what terminal objects are, initial objects, products, and co-products. And talk a little bit about the supertype length calculus and how its syntactic category has products. And I told you that to get any further, now we have to start thinking about morphism between categories themselves. So we're going to talk about that today. Those are called functors. Kind of like the word function, but for some reason they're different. So they're called functors. And since I just want to give the definition of what a functor is, so the kind of variable that I use for a functor is going to be something like capital F, maybe capital G, if there are two of them. A functor F from a category C to a category D consists of the following information. So first we have some data. So we want to send things in C to D. It would be like relatively what you would expect. And we wanted to preserve the structure of the category. So it's going to be something like group homomorphism or some kind of something that preserves the structure of C. So first, the first thing we have in C are the objects. So we have a function. Let's call it ob_f from ob_c to ob_d. So remember, I'm being a little bit vague about what exactly ob_c and ob_d are, but they're something like a set. So when we want to map this set or type or something like that to this one, the appropriate thing is a function. Yeah.
So ob_f is not a set of things, like ob is doing something different to f than what it's doing to c and to d.
Ob is not doing anything, it's just notation.
Okay.
Yeah. Yeah, so, or maybe, it's, okay. In the definition of C, there's one field that's always called ob_c. And definition of F, there's one field that's always called ob_f. That's a different kind of thing. Because this is just like a thing in itself, and this is going to be like a bunch of functions. So it's the function that corresponds to the ob part. Okay, so we have a function like that. And then we want to have functions from the morphisms to the morphisms, of course, because that's the second kind of thing that makes up C and D as the second field, the definition of functor. Now we're going to have two functions. Let's call them f, x, y from C x, y to C fx, fy for all pairs of objects x, y, and z. Like everything in category theory, this is nicely formalized in a dependent type theory. But of course, this thing is dependent on the f here. Or the ob_f, right, that you get here. Okay. So we match between the objects. We have a function that turns the objects of C into the objects of D. And then we want to turn the morphisms of C into the morphisms of D. But the morphisms go between the objects. So this function has to be mediated by the function that turns the object of C into the objects of D. Yes.
So I'm wondering, like, what category are we working on when we're like mapping across categories? I think that's something that's always interesting.
Yeah. So depends on what your choice is for these things. But let's just be simple and say that they're all sets.
Okay.
So these are sets. So this is a function. How I use the word function, I mean a morphism in the category of set. Or it also be a morphism in the category of set. Use the same word, so it's basically. And here, let's say we also want our foundations to be set. But then these things are sets. So this is a set, and this is a set. And that's why I call this a function. Because it's a morphism in the category of sets. Does that make sense so far? Okay. So the next field concept, the next piece of data in the definition of category was the identity morphisms. So we want to also map the identity morphisms to the identity morphisms, sorry, the identity morphisms of C to the identity morphisms of D. So maybe actually I should. I'm making a lot of noise. Okay, so I'm going to write such that if we map the identity on some object X in C, we want that to be the identity on F of X. So we want the functions here to preserve the identities. Take the identity on X, the identity on Fx. And similarly, we want it to preserve composition. We want to have, if we take Fx of some composition, G circle F in C, we want that to be, let's see if I can do it correctly. We want that to be the composition of what we get when we take F and G into D separately and then compose them. Yeah?
The first composition is on C, and the second composition is on D.
Exactly. Let me write here, so I'm thinking of F and G as being two morphisms between these objects X, Y, and Z in the category C. So we can first compose them in C, and then turn them into a morphism in D. Or we can first turn them into morphisms in D, and then compose them there. We want those two things to agree. So we have functions that turn the objects of C into the objects of D. Then they turn the morphisms of C into the morphisms of D, in particular in a way that preserves the starting and ending points, the domains and codomains. And they also preserve the identity and composition. Make sense? Okay. So now I want to give you a tiny exercise. Maybe you can think about it. So one nice fact to check is that, well, in the definition, we ask that functors preserve a lot of stuff. But although we need them to preserve it, they usually preserve more stuff. So in particular, one thing we can prove now is that functors preserve isomorphism. So if the guys are isomorphic in C, and we have a functor F from C to D, then they're still isomorphic in D. And that's good because I told you that isomorphism is a notion of sameness that we care about in category theory. So it would be like really wacky if our notion of morphisms between categories didn't preserve the notion of sameness that we use. Usually morphism functions preserve a problem. Okay? And indeed, functors preserve isomorphism. Okay. Yes?
Did we intentionally skip one of the items in the definition?
I don't think so.
Okay.
No, this because it says 1, 2, 4, 5.
Excuse me. Okay. I guess to touch that was the third line. Thank you. Okay. Okay. Yeah. So functors preserve isomorphism. So maybe I'll leave write this precisely to you guys as an exercise. But let's think about why that is. We just draw this little picture here. So if we're in C, and we have an isomorphism between X and Y, okay, so we have F and F inverse between X and Y, then we have a functor F, and we apply it to this guy, then wondering if I should draw actually a more complicated picture. Then what happens is like we just, apply F to the whole thing. Like in particular, if we have like a diagram, like this, I don't know, something crazy. C-H-I-J, something like that. And we apply, we want to think about what happens in the diagram under the functor F. We want to apply the functor F to this diagram. Then we just slap an F on everything. And that's a functor in the new category, sorry, that's a diagram in the new category D. Yeah.
Just notationally, we're just kind of eliding the X and Y. When we were slapping F on everything in the diagram, we're sort of implicitly saying, oh, this is the particular functor function from X, for X and Y fixed, and
Yes.
Y and Z fixed. So,
Yes. Thanks for that clarification. Yeah, so I'm thinking about, I guess this is not really very computer scientific, but mathematically, we want to think about the functor as doing things to the object in the morphism. And we really want to talk very precisely about the components, then I would write ob F and F as Y, so usually I suppress that, so I just write F all the time. Okay, so in particular, like if we have some diagram in our category C, we're going to just slap the whole thing with the functor F. We know about a functor and we're interested in what it's doing to the diagram. Because we can take F, the component of it ob F, F turns all the objects into objects of D, and then they turn all the morphisms into morphisms of D, and they still go between the appropriate things. Okay. And the diagram, if the diagram commuted in C, then it still commutes in D, because the inverse composition. So if we have an isomorphism, then we can slap the whole thing with F. And then we just need to check that these two compositions are probably too small. That these two compositions equal the identity. So we know that, maybe I don't just start finishing the proof, because actually it's kind of nice to see how this kind of calculation works. So we know that F preserves composition. So when you start doing calculations, I think here there's a lot of heavy notation. Instead I'm going to suppress these indices and the odd thing going forward. So now when we look at something like this, we can just pull the F out. So like on this side, so I can write that this is F of F composed with F inverse. We just pull this F out. Okay. And then I know, okay, so I know that F composed with F inverse is the identity because I'm starting with an isomorphism in C. That's part of the hypothesis. So this is F of the identity on Y. And now I know that the functor also preserves identities. So then I get that this guy is equal to this guy. Make sense? So we can just, if we have a composition, we can pull out that. Like composition commutes with a functor, so to say. And if I see a functor preserves the identity, then I know it's still the identity. And of course, this equation works similarly, and we review the other details. Okay. So now let's think of some examples of functors. We always need examples. So given an arbitrary category or pair of categories, like what is the simplest functor that you can think of? Identity, yes. Identity is always the simplest thing. So we have an identity functor on an arbitrary category C. And what should this do? So now I will write the ob and the subscripts, because I want to supply the data of this functor. So let's call it, some functors are often capitalized, so let's call it id sub c with a capital I. So ob of id sub c, so this should go from ob c to ob c, which is the definition set. And what should it do if I'm calling data ID?
In each object to its own.
Yeah. So it should just take some object of C to its own. And then the morphisms, so I have double here. So if I want to ask what it does on morphisms, then I'm looking at C x, y, and you can map it to the exact same thing, C x, y. What should it do? Maybe you guys can call out.
Just take it to the same place.
Yeah, it should just do nothing. Right? If the identity, if the things are the same, it should just do nothing. It should also do lambda x dot f. Okay. Say this is lambda f dot f. Just does not. Okay. And now we need to check that it preserves the identity and the composition. But what do you guys think? Is that obvious? Yeah, it's obvious because it does nothing. Right? So it preserves everything. Right? So it definitely preserves the identity and composition. Okay. So let's think of the next example. So we're talking about identity functors. Can anyone guess what the next example is that I want to tell you about?
Reversing, not reversing, reversing the direction of all the arrows.
I don't know about that. That's hard. There might be some hypothesis for that. But if I have two functors, so here's an example. Yeah. So following the pattern, right? So identity functors, and now I'm going to talk about composition of functors. So if I have an f from category C to a category D, and I have a functor g from a category D to a category E, I can compose them. You have a functor g, circle f, from C to E. Okay, and so what should this do? So ob of g circle f should be a function from objects to the objects. So what should it do? Maybe someone who answer so I can check everyone is on the same page. Yeah.
What do you mean by what should it do?
So it's a function. Give me a definition of this function.
It would be like you take a lambda. Another lambda. No, I'm sorry. Yeah.
So just one guy x here,
Yeah.
and where should I send it? Someone else is raising their hand, I think? Yeah.
Is it just going to be G composed with ob f?
Exactly. So I know how to send ob C, maybe I can write it in a different color. So I have here ob F and here ob G. Those are two functions. So I can just compose them as functions. So if I want to write it in lambda notation, I can write lambda dot x of ob G of F of x. Or maybe just write an ob G circle ob F. then what about, F, or G, circle F, X, Y. So, just following the definition, this should be a morphism from the arrows in C, from X to Y, to the arrows in G, from, yes, now generate GFX, GFY, so suppressing the up thing and the circle.
And the answer should be,
Oh, yes, thank you. Okay. Okay, and now what should I do? So let me write something in the middle, in red. So what I already have for my hypotheses is, well, F. So F gives me a morphism from this guy to fx, fy. Is that readable? Okay. So this is f, xy. And then g, fx, fy can turn this thing into gfx, gfy. Exactly, yeah, it does function composition, so we just compose these two things. But I guess there's a little bit of thinking involved, because, well, the f can turn this, like we have to think, wait, what can the f do to this? So it turns this into this. And then we have to plug the right things into G, we have to plug in the fx and the fy into G, and then we get out something like this, which is exactly what we want. Yes?
Do we need to spell it out so that things line up, right? Or if we just write the composition, will, arguments go where they need to go?
I'm just doing it on the board, so it's up to me how much detail I want to provide. Yeah. Yeah, I mean, maybe a group could figure this out. So, yeah, so I want to say that this guy is just going to be G, Fx, Fy, composed with F, Xy. Okay, does that make sense? Okay, so now we need to check that it preserves identities and composition. Well, what do you guys think? Do you think that will work out? Yeah, and why does it work out? I mean, just in a intuitive way.
function composition.
Yeah, so we want F, we hypothesize that F is a functor. So we hypothesize that F preserves identities and also composition. And also we hypothesize that G preserves identities and composition. So if we do first F and then G, right, it's going to take identities to identities to identities. Right? And then similarly for composition, F is going to take composition to composition, and then G is going to take composition to composition as well. So the composition of F and G is going to take composition to composition. Does that make sense? So they're both preserving the same kind of structure, so when we just do one after the other, we're going to get preservation all the way. Okay? And maybe if you want to check the details, that's a good exercise. Okay. So now I've shown you identity functors and compositional functors. So what can you say now? What structure do we have? We don't have all functors floating around, but how can we package them up now?
Category.
A category, yes. So we have a category of categories. I told you, like last time, we saw that we can define products in terms of terminal objects, and that all the concepts are all like kind of eat each other, and we see kind of another way in which the concepts are eating each other. The categories, they assemble into a category. Okay. I don't really want to erase anything. Maybe I can erase this one. the category of categories cat has objects, categories, and morphisms, functors. So, like the categories, we might call them C, B, E, etc. Those are our variables, and then the functors are going to be functors like this between two categories. Yeah.
Does cat contain itself as an object?
Very good question. So you might know that if set contains itself, then we get like Russell paradox and stuff. That's not good. So there are kind of, in my opinion, boring fixes to this kind of paradox that I mentioned before, where you can say, okay, I fix a cardinal, and then I can have the set of all sets that are smaller than that cardinal. So cardinal is the size. Or you say like, okay, I have a class of sets or something. That's not a set, so you can kind of stratify the size of things. And here, there's a similar problem. If cat really contains itself, we can get a paradox. But yeah, so if you want to be precise about it, you can say that this category contains all the categories smaller than some size. Okay, so that shouldn't get in the way of it. It's really a category filled with categories. Okay, so this category will become useful because, like I said, maybe one of the things I want to present at least some of the details of is the Curry-Howard-Lambeck correspondence between Cartesian closed categories and, or let's say, at least categories with products and simply type them calculus with products. So I want to say that those two things are the same. In particular, one of those things is categories with products. So I need the categories to form themselves a mathematical object, and the one that they form is this. Okay, so let's give some more examples of functors. Oh, before I erase it, we of course forgot about some things. We need to check that the identity and composition behave correctly. So the identity gives a left and right unit for composition, and that composition is associative. So the identity over there and the composition over here has these three laws. I'll leave it to you guys as an exercise. Okay. So, here's another example of a functor. So, let's consider the category 1. And we'll let it be this guy who they call it before, like A. I guess I mean, that photo rotation, but I don't know. It's just supposed to be the category with one object and no non-identity morphisms. And let's consider just some arbitrary object X and an arbitrary object C. Okay. Now I want to say that there's a functor let me call it, what should I call it? An X like this from 1 to C that picks out X. In the sense that it sends the one object in here to X. Okay. So, what's the data? So, ob X has to go from ob of 1 to ob of C, and what should this do?
It just lambda x and then, sorry, lambda whatever, and then returns that x.
Yeah, we could do lambda x dot, yeah, lambda y dot x. So it just sends everything in here, there's only one guy, x. Yeah,
I think I'm a little lost on what the bracket X, or what's the orange means. Like, I understand that one is just the category that is just one thing, but I'm having trouble with C.
so C is just an arbitrary category.
Okay.
So x and c are just variables, which is arbitrary, and one is something specific. So maybe I am giving this definition because, like, in programming, when you're doing functional programming, terms or values in a type in math 4 are listed as functions out of the unit type. So we have the same kind of thing here. So we want to, given an object of C, we want to have a functor from the unit category to C that picks it out. So on objects, we send just this guy to X. And on morphisms, so then I'm going to say, yeah, so what should I write? Let's say YZ goes from 1 YZ to C X, Y, X, X, Z. Well, what's X, Y, and X, Z? Yeah. There. That's X. And then what should I do? What should the function do? Yeah.
We just like send all of them to like the identity.
Yeah. Let's send all of them to the identity. So we should do lambda f, let's say, to the identity on x. The identity on x is definitely something in here. Okay. So what we really want to think about is we have our category 1, that's just an object, and the identity on that object, but nothing else. And we want to map that little diagram, little picture, into C. We want to send the object of 1 to our value x, and the little identity morphism that's somewhat invisible to the identity on x.
Do we need to write y and z because one only has one element? Do we need to differentiate them?
Yeah, so mathematically, a real mathematician would not be so precise, and they would just say, okay, the only things in here are A,